What is life? How did it start? Is there any out there beyond Earth? And what does a computer have to do with any of this? My name is Kosta Michaelidis. I'm a facilitator with Knowinnovation, spelled K-N-O-W Innovation. It works better written down. And today I am here with Dr. Lee Cronin, founder of the Cronin Lab and Digital Chemistry and Computation, founder of two companies, Deep Matter and Chemify. He is a chemist, conscious human being, a thinker, a tinkerer, a gentleman who today is bound to make your brain go, what? Lee, welcome.
Hi, how's it going?
Pretty good. So Lee and I met in a bland room in a DC conference center many years ago, a workshop hosted by NASA, with a score of astrobiologists and others attempting to reimagine the search for life beyond Earth. And I thought it might be fun to start by just remembering, recalling that and picking out some highlights and thinking about that event.
I mean, do you want me to tell you what I remember, or you want to draw on something particular that you remember?
No, go for it. What was your highlight?
Well, I don't know if it's. I think I was really impressed that they were interested, and then I was a little bit depressed at the beginning, where we were going around the same old. What is life? Can we use NASA's definition? And then we started to gravitate away from what I thought astrobiology should be working towards, to this kind of argument about anthropomorphizing Earth-centric life. And then I think there's a moment where I basically just said to everyone, I got to the point, you've known me in these conversations, where I just basically metaphorically took an acid tab and just said, hey guys, what about if we just did something differently for a moment and just imagine that there was another way of doing life, and then play with that. And to my surprise, I didn't get booed out of the room. And it didn't stay for very long. It was only maybe for 15, 20 minutes, but I was quite surprised. I thought there was hope for the community. Mm-hmm. I do think astrobiology is a community, not as a community, the community are nice, but I think the term should die. And I've been saying that a little bit, not just to annoy the people doing astrobiology, actually more to promote them to the next level, get them more resources, get them more focused. But basically astrobiology needs to die to do that first.
Yeah, let's talk about that. So astrobiology must die. So how do you understand the term that, it's being used today? And then what's your suggestion for what we're shifting to?
Yes, astrobiology is a fantastic term. It was basically, I think, coined by NASA, Carl Sagan, a whole bunch of people, Bloomberg and so on. And it's just literally say, look, hey, there's going to be life out there in the universe. Biology, it means life. And let's look for astro life. And that's great. But it was a bit like kind of saying, we want to understand a paradigm that we don't understand, or we want to anticipate a paradigm that hasn't come yet. So astrobiology is more like, for me, like a hint that we are going to be able to talk about that thing in the future, but not yet. And what's happening right now is I think that our technology, our way of viewing science, our way of looking at space travel and getting data from the solar system is moving to the point where we're ready to abandon the narrow terminology associated with astrobiology, or maybe the lack of a paradigm, and say, can we now build a paradigm? And I think that's why I say it must die. Not because, again, anything's been done wrong, but I think we now need to say, okay, to be an astrobiologist, we need to be doing probability, physics, chemistry, computer science, sociology, psychology. Aliens are going to have, feelings too, or whatever it is, but really kind of bring that down a bit. And literally, the main reason to start with is actually we're having a bit like before the standard model in physics. Standard model in physics unified a lot of understanding. I think Fermi invented antimatter just by saying there should be a negative sign here, right? I mean, amazing. Imagine doing that, developing a paradigm and saying there should be antimatter. Oh, look, there is. I mean, that's like
the predictive.
Exactly. Yeah. And so the problem we have right now is we're saying, oh, we've just found evidence of life on Mars. We've done a little metabolism experiment, Viking, definitely life. Yeah, brilliant. Oh, we're not sure. Argue. Hey, look, we've just found a nano fossil in a meteorite. That's life. No, argue. Oh, we've just found phosphine on Venus. No, it isn't. So what you've got these people looking for life, or saying phenomena associated with life, or objects associated with life, without having a paradigm. And it's like saying, I'm going to discover gravity, but I'm not going to know what mass or space is. And so let's just think of the word astrobiology. So astro is looking up. biology means life, but it doesn't really, does it? If you say to people on Earth, what is biology? They will say, it's cells, DNA, proteins, and those type of objects. So now when you say, I'm going to look for astrobiology, the scientist who's looking out there will look for DNA, proteins, and objects on other planets. And that is, I would say, a priori nonsensical idea. It's a bit like saying, I've got a keyboard, I'm going to type, because I happen to be English, I'm just going to look for English. And the Spanish guy is going, hang on. And the French guy is saying, hang on. And so it's very, very Earth-centric. And that is why I think it has to die. Only as a term. Everybody else needs to say, right, we are the foundations of a new discipline. We're about to go from pre-paradigm to paradigm. We are the architects. What do we need? We need a standard model for life in the universe. We need to look at what exo-life, which is what I'm calling it, because there are exoplanets out there. Those exoplanets will be in one of 4 states. They will be dead. They will be prebiotic, coming alive, maybe, if we can. They will be living, and they could be living and technological. So you think about it, all the exoplanets we can see right now, at least from further existence of, are in one of 4 categories. That's just kind of mind-blowing. And then when you say, right, okay, if all these exoplanets are in one of these 4 categories, how do we tell the difference? And we can't go looking for, for random signature. We need to start doing this statistically. And it's a bit like saying, it's a bit like going from the sun god. I mean, I probably shouldn't bring religion into it, but what I'm saying, what am I trying to say? So it's a bit like, imagine I'm looking up in the sky and I can only see the sun. And I say, I need to worry about how did the sun form? So I obsess about the sun. I just study the sun and nothing else. But suddenly I look up and there's a billion stars and I can do statistics on stars. I can look at stars that are born, stars that are dying, stars that are big, stars that are small, stars that are becoming black holes. And I go, suddenly my understanding of the concept of a star is universal. And so right now, I don't think astrobiology can ever be universal. And so we need to develop that standard model. There's a kind of rather long-winded takedown of astrobiology, but I don't mean to take it down. Again, it's just a word. If you all love the word and you want to keep using it, fine, but let's decouple our Earth bias to our universal bias.
So, okay, just a question here, and we're in the realm of hunches because we don't know, we don't necessarily, we don't observe life beyond Earth. So do you feel, so life is the superset, biology, or life as it is here on Earth, is a subset of that. So now the superset is hypothetical. Do you think it's something like, let's say, different sorts of terrestrial vehicles? So on Earth, in our human civilization, we have a variety of terrestrial vehicles: bicycles, tricycles, cars, electronic cars, the little stupid automated things with the wheels where you lean forward. What do they call those? Hoverboards, trucks, tanks, et cetera. It's, what is it? Tens, maybe 100 different types of terrestrial vehicles. And then one of those is the one we're super familiar with. Let's call it cars. So if you live in a place with only cars and you go out there and in other terrestrial settings and you look for quote unquote biology, right? You're looking for other cars and you come across a tricycle, you might not notice that it's also a terrestrial wheeled vehicle. And so what I'm asking is, how much of a superset subset do you think, like carbon-based life as it is with proteins, et cetera, here on Earth and DNA, versus the superset life in general? Like what proportion of life do you think is like life on Earth?
My honest answer, I have no idea.
Okay, all right.
My answer to, if I was going to try to, so, but always that's fine, because I'm an expert in a very small number of things that are probably not very interesting to many people in the world except me. So I always find it fascinating when people opine on things they don't not really qualified to opine on. So, but let me work forward using my own rationality. And what I'm interested in saying is that I would like to know more about the composition of the exoplanets. So what I mean is, how far are they from the sun, their relative star? What is their elemental composition? And how many planets, like, is Earth a rare planet in those? Because then you can say, right, starting with those starting point of Earth, time, some carbon, some water, some minerals, we're going to get, life is likely to emerge using carbon, because it seems, what happened here, right? But are we going to use proteins and DNA? No, absolutely no chance. That the idea that the code for proteins and DNA is somehow written into the cosmos is the biggest fallacy ever. And it's because of the combinatorial explosion, right? I think we have to understand we're a one-off and that doesn't mean we're a one-off of life. We're just this type of life. But it would be interesting to know if there's a tree of lives, right? To say, right, they're the silicate, they're the silicones, there's the carbonite, whatever, and say this, and you guys, you life forms, your planet had this type of history. And you can probably see the planetary history in the life form. And this is one of the beautiful things about life on Earth. It absolutely is a recording of the change of Earth's composition environment for the last 4 billion years. So I think that I'd like to think that there are other rocky planets out there, like Earth, and there is, and carbon's a fairly abundant element in the universe compared to some things. So I think it's reasonable to suppose there are other carbon-based life forms, but are they going to be like using the same toolkit? No possibility of that happening. In fact, there's then the same possibility of me having someone being exactly me on planet Earth and the 7 billion odd people out there. There might be people that look very, almost like me, better looking, smarter, fitter, all the good stuff, but there's no one going to be identical. And that's, I think, that contingency, because I'm genetically, as far as I know, as long as I've been cloned, unique. And that, I think, is really very difficult for chemists and biologists to get their head around. Physicists and statisticians do accept it, but then they get kind of caught with the way they've been taught about mathematics, infinity. They come up with all sorts of nonsense that they don't think deeply enough about, because the universe is not infinite as far as we know. It has a finite amount of resource, and that means there's a finite number of things you can do. So you're going to do the obvious, the accessible, and the contingent. And I guess, and that's why I'm pretty confident there is life elsewhere in the universe, but it doesn't look like us.
So let me see if I understand correctly. So let's theorize, or let's hypothetically, you have a set of planets, hundreds, thousands, millions, and each of those planets, and let's rewind time down to 0 or 100 million years, or wherever a decent starting point is for this thought experiment, and you have only simple chemistry happening on those planets. So it's only physical processes so far. We know there's nothing live at the start.
Yeah.
And so you have all these planets, and let's say you can observe all of them for 1 billion years. You observe all of them over the course of 1 billion years. So what you're saying is that in some small subset of them, self-replicating RNA, DNA, proteins will manifest life. And then in a variety of other ones, something else will manifest life. I'm using the word life on purpose here. So some other system of either self-replication or complexifying, like something that complexifies the chemistry.
Yeah, I mean, I think that the solution of RNA or DNA, is it precisely contingent upon the base pair atom makeup? Maybe not. So there may be variations, but I do not think there's going to be another life form with 4 base pairs of our base pairs and 20 amino acids. I just don't think.
Yeah.
I think they're going to be different, and you're going to see it. Now, if we find life on Mars and we prove we haven't contaminated it from Earth and it looks the same, well, I would probably argue very strongly there was a common origin, and that a lot of the chemistry for life was cooked up on Mars and flung to Earth. But I'm pretty sure, I mean, you think about it, it's just even the simplest molecules that we say are taking part in biology are really complex. You think about getting a royal flush, what the chances of that are, or a sequence of cards, right? If you have 52 cards and you want to basically get the one particular sequence, well, it's an unimaginable number. And so and here's why. And this is the thing that, and I'm writing a paper on this right now, which is basically says that the way that chemists are so biased and they think that their reactions are somehow special. Their reactions are not. In fact, I would go for argument to say that reactions don't exist, really. What exists is the following. Quantum mechanics exists and reactivity exists, so the periodic table. Then you should imagine there's this massive lookup table of all possible reactions that could exist at every pressure, temperature, gravitational constant, composition of elements. And that basically the reactions we have on Earth are a product of 1 atmosphere, 298, 1 G, the elemental composition, and the history as well, because asteroids hitting in, asteroids nick. I mean, the astrobiologists, or not astrobiologists, origin of life people have to have a massive meteorite of phosphorus come and land on the planet at one point to basically, there's all sorts of weird things we have to invoke, and we just don't know. And so I would say that if you understand and accept statistics properly, the chances of us having that composition, again, unless there's some magic God, if you believe in God, if you believe in RNA, I'm going to be very controversial. You have to kind of be religious. And that really blows people's minds, because they think I'm just trying to make fun of RNA people. I'm not. I'm just saying, look at how tricky it is to get to RNA. They say, oh, no, but the chemistry gets there. And I was like, okay, show me the rate constants. It's because of 1 atmosphere, 298, liquid water, temperature. Go to Jupiter. Why is there no RNA there? In fact, how do we know there's not life on Jupiter? Well, okay, we would like to see technology and odd things happening, right? But how do we know? How do we know? We haven't been there. It's quite interesting that we have not landed on Jupiter, so we don't actually know what's going on there. I suppose we can probably say, well, there's not that much going on because of the pressures are so extreme. The thing that I think is universal for life is we need to make chemical bonds. And the problem about Jupiter is it's quite hard to do stuff.
So, yeah.
It's metallic and so on.
So I want to take us back to the event where we met and recount Michael New's introduction, because I thought it was really good. And he coined something called emergent. I don't know if he coined it, but he was talking about emergent features of life. And then we could peg emergent phenomenon, because I know you have something to say about that. But also what would be interesting is to try and think about what they might be. What might be a variety of emergent phenomenon, things we don't understand yet about life. And so if you were to go to Jupiter, which one of them might you find that's common to the one here on Earth? So the conference on reimagining the search for life beyond Earth was kicked off by Michael New, who is, I think he is now the deputy director of research at NASA. I don't remember. Then he was deputy director of astrobiology at NASA. So he talked about an artifact that was found by archaeologists. It was a stone, and there were some etchings in it. And those etchings, archaeologists couldn't figure out what they were. Was it art? Was it a language? Was it was it some sort of mathematics? Was it an accounting? They couldn't figure it out. There were a bunch of etchings, but it was difficult, mysterious. They didn't have other examples of these etchings. So it sat in a museum for a long time. And at some point, a statistician came across it, took a photo, looked at it, analyzed it, and said, oh, I can tell you what this is. He said, well, archaeologists have been looking at it for years. How are you going to tell us? Well, have you had a statistician look at it? And so he did a histogram of each of the etchings. So okay, this one appears 3 times, this one appears 5, this one 35 times, this one 6, this one 1, this one 3 times, etc. Looked at that histogram, and the histogram, it wasn't a normal distribution. It wasn't anything else. It was quite similar to other alphabetical languages. So in alphabetical languages, lots of letter E's, lots of A's, occasional Z, occasional Q, occasional X, some C's, some B's, some S's, etc. So that histogram of number of times each of the letters appear is somewhat distinct to alphabetical languages. So said, okay, we know it's an alphabetical language, or it's quite similar to other alphabetical languages. And they managed to use that information to figure out what it was. And it's either linear Minoan A or linear Minoan C, I forget. And they managed to translate it, which is pretty cool. So he gives that intro, and he's saying, okay, so we're looking for life, but we're looking for liquid water on the surface of a planet that's a certain distance from its star and somewhat the size of Earth. It's like, why we're looking for other us. And there might be other us somewhere out there, but there might be 99% living other things that have nothing to do with us, and we'd miss all of them. Because we're looking for English, out there, and there might be Minoan and Latin and Spanish, like you said earlier. So what I'm curious about is the emergent features. And so I know the one you like to talk about, I'd love to talk about assembly theory, is complex chemistry as an emergent feature of life. It's really cool. But I also wonder, what might some other ones be? Are there other emergent features of life that are reasonable to assume?
Well, I think that, molecules are just one manifestation. I think emergence, I used to love the term emergence. I grew up in the 80s and 90s with chaos theory. But the reason why I have something to say about it is that it got to the point where it started us, again, it was pre-paradigm. It's a pre-paradigm, and that's why I would like to replace it with a more concrete term. But let's talk about what are emergent features. Well, language is an emergent feature of life. It's not to do with molecules, social structures, things that undergo locomotion in a coordinated way, planets that anti-accrete. So most planets tend to be dragging asteroids into them. And this is one of my colleagues at ASU, who is a physicist, but which she would always point out, Sarah Walker, that isn't it weird that, Earth is actually throwing stuff out of its gravity well? You're like, that's a weird. That would be something I would look for if I was an exoplanet person. I want to find exoplanets that seem to be lobbing stuff into orbit. That's an interesting thing to look for.
Yeah, or avoiding things that are headed into their orbit. Like if there's an asteroid headed for a planet and then it switches trajectory, someone did something somewhere.
Yeah, if you can ascribe causation, because that's really hard. And one of the things is ascribing causation. And another thing, I suppose, would be making technetium. Technetium is a weird element, right? Technetium is an element. It only has a half-life, or making really radioactive technetium, which gives off a very intense radiation. That only has a half-life for a few hours. So to make that, you actually have to build a nuclear reactor and purposely do a bunch of things. So what am I getting at? There are some technological objects that, technology is really the ultimate of your way up. And if you can think all the way down, so the lowest is probably, molecules, and then organizations of molecules in cells, and then multicellular organisms, then organisms that can move, then organisms that can abstract and invent and make. But to be honest with you, all of the emergent phenomena we talk about in physics, they're not really that interesting. They're just like, yeah, there's lots of stones in the bucket, and look, there's this thing happening. Or we can see a hurricane, isn't that really interesting? Or there's a black hole developed, isn't that really interesting? Sure, but the number of parameters needed to describe these objects is very, very small. And so we can come to that in a moment if you want to talk about emergence. But yeah, so there's all this plethora of things associated with life. So molecules at the lowest, and then basically political systems disinforming other political systems through social media at the top. Or maybe I think the ultimate evidence of life in the universe is TikTok. But I'm pretty sure there's no TikTok elsewhere in the universe. But I'm sure actually more common than, I'll make a radical prediction, more common than carbon-based life will be conscious entities wanting to video themselves.
That's funny.
What I mean is there'll be more civilizations in the universe making devices to video themselves than will be civilization or life forms built out of carbon.
That would be fast. So what's fascinating about that is that there's a divergent component to this, which is that the chemistry in the universe creates lots of different types of things. This is evolution, right? It diverges, creates lots of variety. But the more interesting thing is that it converges too. So certain things emerge, like communication, transport, motion, certain types of organization, things videoing themselves. Consciousness in theory is a thing that emerges out of this process. That's really cool. Okay, so 2 questions. I guess you can take them in whatever order you choose here. I don't know how you want to explain this one. But the 2 questions I have is, what's happening in chemistry in our technologically accelerated world? And then what is assembly theory?
You pick. Which one would you like me to talk about first?
Let's talk about assembly theory.
Okay, so assembly theory is something that I kind of been trying to get to grips with for since I was wanting to work in origin of life, or not origin of life, understand what we were, almost like I was a kid, I think, right? And I can explain the basis behind that. But what I felt was missing when I always wanted to know what life is. And I was all fascinated that people kind of know what life is. They all know what life is, or that some people don't care. And there's lots of people working origin of life that don't actually care about the problem of origin of life, that just want to make molecules consistent with what we know in life now. And I probably wouldn't call that origin of life, because I want to be constructive about it. Because is it worthwhile that somebody makes RNA? Yeah, it's brilliant. We should do it. But I don't think we should say that's the answer to the origin of life. We might say, isn't it cool that we can understand minimal routes to making these molecules? So anyway, what I wanted to understand is that there was this thing that life seemed to do, that I was always noticing, that life was creating states. It was creating kind of ideas. It was creating imaginations, abstractions, right? Something, for human beings. But then you can go down and say, well, look, what is life doing that is a bit more kind of general, right? What is a common characteristic of life? And I spent ages trying to think about how evolution worked and selection got going. And I was really thinking about how the universe is almost like able to create its own future in a living system, that that living systems are able to act on matter causally to make more states. It's a bit weird. I'm kind of mumbo jumboing, but what I mean is, if a universe without life has a finite number, the universe expanding, time is going on, but a universe with life seems to be able to create additional possibilities. And I couldn't capture that. It's like, it seemed to be like universe is combinatorial, but the universe with life in it is combinatorial plus plus plus. So I was kind of like, let that go for a couple of years. I went to an artificial life meeting, and then I went to origins of life meeting, talking to people, thinking, trying to parse what was going on. And then I got thinking, well, there are 3 different thought experiments I was doing. One which was, I've got this big molecule I make, and I put it in mass spec. Can I tell for certain that big molecule was made by biology or hadn't been randomly formed? So that was one thing. The second thing was, how can I use information to construct objects, and where is that information? And the final thing, which is like, how do I quantify complexity across loads of domains? Because complexity in mathematics and computer science seem to be different complexity in biology, and no one could give me a measure. It's all emergent, right? And so I was really deeply confused, and I realized that also so were lots of areas. So then when I carried on my mass spec thought experiment, I thought, hang on, well, I'm a molecule, I'm in a mass spec, I've got a well-defined molecular formula, I've got a structure, a mass, and what I'll do is I'll weigh me, so I get a molecular ion, so I get the peak for the actual molecule. How much do I weigh? But what I can do is I can fragment the molecule, a bit like I could take maybe, let's say, a really intricate piece of art. Mm-hmm. And let's say I take that piece of art and I take a hammer to it, and let's say I make 1 million identical copies. I take a hammer to it and I hit it ever so slightly to break it, but not so much to smash it to smithereens.
Right. You're not putting it in a blender. You're hitting it with a hammer. Okay.
Exactly. Because the artist has worked on it, shaped it, maybe it's a person, of a man, a woman, a child, or something, or a tree. So it then falls apart, and you can see bits that have come together. And then you look at it again, and go, right, I'm going to make another bit and hit it again. Let's see how it fractures, and do that. And then you've got all this pile, and suddenly, let's say the person who owns the art museum is coming back, and they want their piece back together. You're like, shit, what is the minimal route I can take to glue this thing back together? And so assembly theory is basically that. Assembly theory is like, when I take a complex molecule has low symmetry, and I hit it, it falls into lots of different parts. Now, if I keep hitting it again and again and again and again, I get all the way down to the atoms. Now, how do I turn the atoms back into the molecule? And the shortest path to do that is called the assembly index. Now, I'm going to bring this all back down to earth, because I'm sorry, I'm not thinking clearly. I'm going to take the word abracadabra. Abracadabra has 11 letters, and it has 5 atoms: the A, the B, the C, the D, the R. With those things, I can make abracadabra. So now what I'm going to do is I'm going to take abracadabra, I'm going to randomly chop it apart. Now, if I'm really, really boring, I just chop, and make the 11 letters. Okay, so I make those cuts. Or if I'm basically lazy, I can just cut it randomly, and then look at the parts, say, well, are you different or the same, and keep cutting and taking the parts that are different out. And every time I have a different part, I put it to one side, and then I cut it down again until they get to the base of the 5 letters. So then you find that although abracadabra has 11 letters in it, 11 letters in the entire string, to make from the pool of 5 atom letters, I only have to take 7 steps to make the word. Don't have to take all 10 steps, right, to make the 11-letter word.
Because you make abra, and then that chunk can repeat.
Yeah, exactly. That's exactly it. So that's what assembly theory is. So when I started explaining this to people went, that is the most obvious thing ever. Or NASA did, right? NASA does. That's obvious. We've known that for 50 years. And I was like, really? Where's the paper? And they said, oh, no, it's just obvious. And then when I said to some other people in complexity theory, they just said, oh, no, that's already been done here in logical depth. Anyway, so I carried on probing, and it turned out that really assembly when I did in the mass spec Dankin experiment, did something very, very special. It wasn't just breaking a molecule apart, because if you have a molecule with lots of parts, of course, you find lots of molecules with it's statistically probable you're going to find a molecule that's formed randomly that's complex. The statisticians, the complexity theorists know this. What I really lucked out on with assembly theory and mass spectrometry is when I have the molecule in the mass spec and I see it, I already am seeing at least 10,000 identical copies. So let's do the thought experiment again. Say, right, now I've got this molecule and I'm breaking it apart. It has all these parts. And I have at least 10,000 copies. What is the probability that if I've got a molecule, say with assembly number of 5, that I can make it easily, randomly? Fairly simple. What about 10? And what about 15? And when we validated assembly theory, remember, assembly theory just says that it tells you the shortest route to make an object probabilistically using repeat units along the way to make the object. Okay, that's it, that part. But then, if you can find it in abundance, what is the probability of that? So what you do is you say, right, I'm going to do a model, take a random walk. I'm going to allow myself to have assembly number. As the assembly number goes up, I've got this tree that keeps going bigger and bigger and bigger. It turns out, if you have a molecule that can do normal reactions, right, just normal chemistry, and just we can factor some little bits of overlap, right, to make it really simple. If you go to 15 steps and you make, and one molecule has 15 steps, all things being equal, the chance that that molecule can form more than one time is 1 in 6.022 times 10 to the 23. 1 in a mole. So to put into perspective, if you took 18 milliliters of water, maybe like a shot size, in that water, one molecule is 1 in a mole. So if I say find a molecule that has an assembly number of 15 or higher, the chance of that being created randomly is less than 1 in a mole.
And here randomly means purely with physical processes, like without conscious intervention.
Exactly. No chemist, no biology, just stuff going on. Now, when I first introduced this, the chemist said, oh, this can't be right. You know, of course, there's chemistry that can make molecules, right? They're more easily because the structures overlap and it's easier. And I'm like, sure, of course, right? There'll be some of this. There'll be some complexity. How much do you want? It's just a scale now. They went, no, we're not going to accept the scale. And we had this really very funny discussion for a number of years, actually, where people just would accept the concept of the scale. And you know what I did? I just went and said, you know what? Let's do something interesting. I'm going to go and take a load of molecules. I'm going to write my algorithm. I'm going to break the molecules up in the algorithm like abracadabra and give them assembly indexes. And then I'm also going to go and buy some molecules, and I'm going to measure the mass spec. And then when I measured the mass spec and I break the molecules apart, I looked at the assembly indexes, I got a correlation, like almost 1-to-1. I was like, whoa.
That's the kind of predictive thing. Yeah, that's where you get, okay, here's our theoretical thing. Here's what it would predict. You do the experiment, you observe, oh, wow, it predicted the thing. How close was the prediction to the...
There was about, it was about between 85 and 90%, right? And obviously, and this was mass spec. And with mass spec, because bonds break not uniformly to do with the structure, there's a little bit of variance. But then when I then took another technique called infrared, which exoplanet explorers are going to use, 100%.
Right.
And then NMR, basically 100%. And I was just like, wow, okay. Whoa. So even if the chemists didn't like it and the theoreticians didn't like it, I had developed the world's first ever measurable complexity metric in any domain, right? People worry about computable, but this is like measurable, like physically measurable. How do you measure the complexity of a car? How fast it can go? How do you measure the complexity of a human being? The therapist costs, you know? I mean, so the nice thing about this is it works because of sorry, you were saying?
The only thing I can think of is computational complexity in computer science. Yeah, big O notation, which is cool. Yeah. But
the problem with complexity in computer science is not actually, if you take the gold standard Kolmogorov type complexity, it's not computable. It's super, just dies. So so you have this idea, but then common goal of complexity is not about, it's about program complexity, assuming a computer program and a compression algorithm. What I'm trying to say, and the computer doesn't exist.
Yeah, you're talking about nature. You're talking about measuring the complexity of something in nature. Yeah.
And this is like in the causal chain, not above it. Computer scientists are the God looking down. Assembly theory produces a God growing up. And hopefully they'll meet in the middle. So then I brought this to NASA, and NASA said, okay, we don't really believe you. We want to do a bit more social work. We'll give you some samples from outer space and around the world, and we'll blind them. We won't tell you what we're giving you. And I was like, because I was like, that's very cheeky. I was like, all right, fair enough. So they gave us like a load of samples. And we ran it through, and one of the samples was like, this is not alive, but it looks weird because it's weird isotopes. So we're like, well, we're not gonna fall into the trap and say it's alive. There's just a weird isotopic distribution, so we think it's extraterrestrial. And then there was another one that looked really weird, which was a fossil. A 30,000-year-old fossil, and then one that was a 1,000,000-year-old fossil, and then loads of other stuff. It turned out they gave us Murchison. Murchison is one of the most complex kind of classes of meteoritic organic extraterrestrial organic compounds. Literally countless millions of compounds in it, and they thought they would definitely fail the test. Nothing with assembly number higher than 12 in Murchison that we could extract. Nothing. So that's kind of cool. So we kind of have now a signature using assembly theory, because now assembly theory, the actual assembly equation is so this is kind of, it's taken me many years to get here with help with theoreticians and Sarah Walker's team and people at the Santa Fe Institute. And that basically the whole story is that assembliness is going to be like entropy, I think. So if you take a box of objects, say I've got a box of molecules, the assembliness of the molecules in that box is equal to the sum over all the molecules times the exponential of the assembly index of molecule I times the log of the number of the molecule I. Now, why is that? Well, if I find a random molecule that's got an assembly number of 1,000 and there's only one copy, it's probably produced by chance. And therefore, there's no information associated with that and no causation. So a log of 1 is 0. So it basically factors out the equation, so there's no assembliness. So what I'm trying to say in assembly theory is not just about the number of parts, but it's about the abundance and putting those two things together. And a really good complexity physicist, a guy called Jim Crutchfield, actually pointed this out to me many years ago and just said, look, you've got to think about the abundance, because when it's random, when it's something purely random, not purely complex, and he's like, the answer is you can't tell. And the only way you can tell is through this number of, so that's why assembly theory is really fascinating in the physical world, because suddenly we're going to have a handle on something that doesn't measure entropy. Entropy tells you something else, that's good, but assembly tells you about the amount of causation or amount of information or machinery that's put into that process.
That's fascinating. So, okay, I'm not a scientist, so some of my questions might be fun, some of them might not be. If you look at basic chemistry, so if you take the most basic molecules, single atom molecules, you have a certain number of them that are possible. You have the 130 something that we know about, and then in theory you can keep fusing things together and getting some more, but somewhere over 100 possibilities. If you have two element connections, or the single element repeating, two atom molecules, and then you go to 3 atom, 4 atom, how quickly do you how much does the complexity grow? Like where would RNA land on, like what tier do some of the...
So basically it gets really damn complicated really quickly. But the nice thing to observe is, obviously, because we know on Earth, we know the chemistry of carbon, we know carbon forms chains. I suspect that silicon, phosphorus, sulfur, selenium, and various other elements can form chains. But when you go up, it explodes pretty quickly. But when you have carbon, nitrogen, oxygen, it explodes dramatically. An RNA monomer, like most amino acid monomers, can be made in the milliuri, kind of in soups. and they have assembly number, I think the maximum, if I recall correctly, but they go between 5 and 12. But when you have an RNA dimer, 2 different monomers together, you get over the threshold. So people go, I can make high complexity molecules in my soup. And I'm like, go on then. And the answer is they can't really. And when they do, they have to put in information because they're shepherding it. They're like, turn off the reactor, stop adding that material. And so so all that assembly does, right? If you do a reaction and you find the highest assembly number molecule, you've either prepared it, like Viagra is a high assembly number molecule, and it's made by human beings with a recipe. You could make DNA base pairs and dimers and so on. You put the information in, but the chances of these dimers and trimers forming in any abundance in the system is quite small. So then you have this really interesting argument where the chemists really did, worry about when I was trying to push this. Said, well, look, you're saying that there was no complexity between the origin of life, and so yet the origin of life is all this complexity. But what happened? And I'm like, that's exactly. Let's ask that together again. What happened? So now, as a call to arms, to say, let's go back to prebiotic chemistry and look for selection in inorganic minerals, directing. Let's use assembly theory and mass spectrometry to do and look, because obviously what happened was this. A chance event, chance molecule, low assembly number molecule, just doing its business, maybe interacting with a mineral, binds in a chance way, and acts as a catalyst on another small low assembly molecule that then gets a bit bigger. And this molecule can act on another molecule, and then they make a cycle, just chance, and at some point you make a little loop, and before you know it, this loop is pumping low assembly stuff to high assembly stuff. Wow. Now the assembliness has gone up. Selection, showing you that selection has occurred. Selection without biology must happen, or the universe is dead, right? Then when you start getting selection here, you keep going up, and on Earth, what did selection do? Well, it created RNA, DNA, protein, cells, and Donald Trump, and Boris Johnson, and I mean, let's be fair, and Angela Merkel. Let's be just all of them, right? Sure. So, and I'm not saying that assembly theory says that there is no complexity and no interest in chemistry at the origin of life. No. I'm saying that if you make your scale long enough, you can know that we really have got life. Because if you don't want the threshold we found at 15, maybe take it to 30, right? Just make it harder. Yeah. Set your limit to be harder. And the nice thing we have now is a probabilistic scale. Then when NASA hopefully flies its drone Dragonfly around Titan with a mass spec, basically NASA are sending a mass spec in a flying machine to Titan to go and look for complex organic.
Flying machine here, you mean flying in the atmosphere of Titan?
Yeah, it's going to be a drone. Okay. It's going to land and hover up and go. It's going to be amazing. I mean, it's a nuclear powered drone.
That's awesome. What are the dates on that? We're looking at 10 years from now?
Dragonfly's taken some slip due to COVID, but it's going to be going in the next decade, I think, next few years, and we'll get to Titan and we'll fly around and sniff it. I mean, it's like Titan is basically in one atmosphere. So I think it's like the same kind of pressure as on Earth. So they're going to have so much fun. It's just so annoying that they can't do it, literally fly a drone on Titan remote.
Like remote. You have to, it's got to be autonomous.
It's going to be autonomous with a little bit of steering, but wouldn't it be great if they could find complex molecules that would go up that cascade? And I'm getting quite a lot of blowback on this, and people will not believe the outcome, but we have to just take them down that path.
So a couple of fun questions here, and I imagine these are the next experiments to do. So one is, okay, you have complex chemistry, so no loop yet that throws things from lower assembly to higher assembly.
Oh, no, we have one.
Right. No, I'm not saying we don't have one, but just theorizing here. So let's say you start with some basic chemistry, and you don't have a loop yet. How many different types of those loops that take things from lower complexity and throw them into lower assembly to higher assembly? How many different ways can you make a loop like that theoretically?
Oh, I mean, they're countless. We've thought about it. I think it's really, really, I think that autocatalytic processes in combinatorial soups are the engines of selection. I'd say that again. Autocatalytic reactions in soups are the engines of selection. And what they do is they compete, right? Because they have a very low memory. Because this is the thing, you've got this. What is the role of this little gloop? Is to make more of the complex molecule of itself, right? It's like literally it's all it is. It is the meaning of life. It is one arms race at the molecular level. You think we're sophisticated? No, we are, but we're still doing the same thing as the molecules are doing. Is that now we have all this other baggage going with it? So there's lots going on there, and then because they exist for a certain amount of time, and the memory is short, so they get killed by changing the environment. The environment switches.
It gets too hot or too cold or anything. Yeah.
So wouldn't it be good? So under those circumstances, the objects that get trapped by chance in a bubble don't die. The other one, and the other ones are gone. So there's no competition. So more resource. So then they can do more high assembly things and get more complicated. And it doesn't take a genius to see that this is how life got started.
Okay, here's the next question, because my brain, does things like this. So the number of possible loops that take things from a base level of assembly up to a higher order, right? And then let's imagine there's another notch up, right? Where things are the same process, just one notch up. They're taking higher assembly and lower assembly stuff and accelerating those even, one tier higher than that. Are the types of loops that can do that second tier thing, are they more numerous because the complexity, the chemistry they have to work with is more numerous?
We're playing with that right now. I think that happens, you have a bit of so what seems to happen is that you have a massive explosion of mess, right? That what chemists have seen. Poor chemists. I mean, I shouldn't really, beat up on the origin of life chemists. They've done amazing things, but they also have amazing dogma. And if I could just get rid of the amazing dogma and say, look at the amazing things, guys, and let's from this. A lot of people gave up at the soup because you just formed a mess and they didn't see how to get around that. And I was thinking, if you get better, what seems to happen is you get simplification. So you put more of your resource in less molecules, but higher complexity. And then but what happens is suddenly they find another niche. They go, I'm now able to react with you and bring you together. Suddenly, boom, and you get explosions of complexity. And I just don't know exactly the dynamics for that. And I suspect that it's going to be a series of oscillations where you get combinatorial explosion, consolidation, with increase in complexity. Then combinatorial explosion, complexity increases again, consolidation. And it might not even happen at the same time. There might be lots of different competing factories. Again, the short answer is we just don't know. But my feeling is it's going to be punctuated in some way. And I'm trying to do it in the lab right now. It's one of the reasons why I invented the digital computer. But we can talk about that in a minute.
Yeah, let's jump right to it. The only thing I wanted to confirm there is, so what you just described might help, the oscillation might help explain why something like DNA-based life forms have come to dominate in this particular, and so forth. Yeah.
So I think what happened there, and I mean, again, there's so many good people working on this right now in Origins of Life, actually, at a higher level, where they're trying to speculate what are the features of these base pairs and how they bind together, how they can create these higher order structures. I've always a bit worried when you do it in isolation because it feels like you're creating the engine for the motor vehicle, but without understanding the conditions, that the engine didn't get created by the process of constructing the motor vehicle, something else happened. And so you've got to just be really careful about the cause and effect there, but I think it's okay. But I think what you can have is you had lots of competition, and then basically DNA is the consensus molecule for genetics on Earth. Isn't it beautiful? In that you had lots and lots and lots and lots of ideas, and you just got to the consensus molecule. And the consensus, why is DNA a consensus molecule? Well, it survives in most environments. It seems to be usable by most life forms that were increasing their complexity. It was, resistant to radiation, resistant to most environmental change on Earth. It was, the origin of life or the establishment of life on Earth was democratic. It was a planetary phenomena. So I think that's exactly how it happened for those cycles, where you basically explore a bit, die a bit, explore a bit, die a bit, and because basically the longer the life form exists for, the more challenges it's going to face. It stands to reason. The more chance events, meteorites hitting, radiation, changes in humidity, changes in pH, earthquakes, fire and brimstone,
Yeah, it's fascinating, and it might provide a basis for defining biological scales. So in a variety of the events we've done, biological scale is something that comes up, but biological scale is just assigned semantically by humans rather than observing it from the ground up. Like, are there meaningful scales of biology that we could talk about and say, well, look, it's this chemical complexity, this point of convergence then leads to this, and then these are called species, or these are called something else here.
We need to wait. We need to wait until we make more life forms. The other thing is, I think that Earth might be late to develop consciousness because the gravitational constant on Earth is too high. Imagine the gravitational constant on Earth was lower. The push to have to go to multicellularity and oxygen.
Gravitational constant, you just mean 9.8 times 2 to the, okay.
You use quite a lot of energy to move around. If that was lower, we might have become conscious earlier, but more intelligent earlier. Everyone's saying, oh, life is so hard to get conscious on Earth. It's like on Earth. Well, who says it? Who says you can't get consciousness and intelligence much earlier?
So let's park what is consciousness, because that's a fun one and we can come back to it. But you wanted to jump to, as a chemist, why take an interest in computation, and what is computation?
Yeah, computation is another thing I'm getting hammered on all of them, actually. It's quite interesting. But the nice thing about getting hammered on new ideas is, I'm not shy. I will kill the bad ideas, and it's like selection. It's like so computation is an idea that's grew out of a very long time, where I wanted to build an origin of life engine. And it's kind of like I wanted to build a massive. In fact, this idea was invented at a Knowinnovation event at the post office in UK Innovation Centre many years ago. The Ideas Factory that EPSRC funded.
Is this synthetic aesthetics?
No. Way before that. So it's one of the first ones. I need to go look at my notes when it actually was. But,
no worries.
But while I was doing a little bit prebiotic stuff, or what I didn't want to do prebiotic, I thought that why don't I just make it the origin? I see the origin of life as primarily a chemical search problem. And I was like, if it's a chemical search problem, all we need to do is make a search engine and get a load of students in the room and say, just do some chemistry for a bit. And I thought, oh, hang on, if the origin of life took 100 million years on a planet, that's going to be one really interesting grant proposal. Say, hey guys, I know there's not much money for science, but I just need a planet 100 million years and all the grad students. So I figured that wasn't going to fly. So then I thought, what I was going to do is I'll design a little modular robot that would do chemistry. Like, how hard can it be? Bit of mixing, bit of shaking, bit of heat, bung some stuff in. Come on, I'm an inorganic chemist, right? Not an organic chemist by training. So inorganic chemists are really chill with making a mess. Organic chemists, if you make a mess, that's really offensive. I have some really top class organic chemists in my lab right now doing drug discovery and stuff. I'm like, just make it impure. And they're like, it's like insulting them. It's like saying you are, you're ugly or stupid or something, or whatever biggest insult you can think of. But anyway, I was like, mix all this stuff together randomly. And I thought, okay, I'll write some proposals on this. And of course, I was doing the work in stealth in the background, wrote the proposals, origin of life engine. Everyone surprisingly said no. And I was like, why is that? So we don't care about the origin of life. And I was like, do we care about aliens? I said, okay, what about if we design robots to make drugs? And it went, that's better. So I thought, oh gosh.
It's the same project. It's the same work. You're building the same kind of machine.
The intention is critically different, because I'm a great believer in not only doing what you say, but having a little bit of an indication it's going to work. So you're investing. I know this is a big problem of academia, like your preliminary data, what you do and all this stuff, but let's not talk about that. Mm-hmm. So what I did is I thought, well, I'm going to design a machine that does all of organic chemistry. And I made fun of myself and my colleagues doing it for about it. So look, I'm going to replace you with a robot. And remember, this is 2012, and it was a fun, right? But they didn't take kindly to it. I did not make friends and influence people. And so I don't regret anything in my life, but had I done that again, I might have taken a more nuanced approach. But actually, I think annoying them was really useful, because they came at me and said, "This is stupid because," and I would be like, "Oh yeah, okay, that's good." And they wouldn't say, "This is stupid because you're stupid." They were nicer than that. And they're stupid because reactions aren't uniform. Stupid because you have too many reagents. Stupid because purification is hard. Stupid because there's too many things that can go wrong. And I got a consensus over some time, and I said, And when I was trying to build my original origin of life engine, I tried to build it in a flow system. Like I imagined that the origin of life was the beginning of a pipe, and then I'd flow the stuff down the pipe, and at the end, a man would walk out, or a woman, right? Or both. Let's be both. Yeah. Anyway, because if one has to come first, whatever I say, I'm screwed. So both come at the same time. And so that's fine. But the flow chemistry didn't work. So when I was thinking I need to design a chemical engine, I thought a microfluidic one. So I tried to do that and I failed because I couldn't get the technology together. And I thought, what am I really good at? Like, I'm really good at things like this, like a beaker, put some stuff in the beaker, heat it up, extract it. And I thought, this is what chemists do all the time. In fact, they're really good at it. I mean, like there's some, and then they're not just really good at it. There is 200 years of literature with this stuff, where chemists would typically work in what I call batch mode. They would have a reactor, and then they would put the chemicals in, start the reaction, number one. They'd wait some time, then they would work up the reaction, so work up, number two. So it actually has some solvent or precipitate or cool down, whatever. Number three, they would then isolate the material, come out, maybe put it in another filter flask, filter it off. Number four, they would purify it. And I thought, hang on, is this some kind of, and I thought this is like an abstraction for chemistry that didn't exist in chemical robotics. And so I persisted with my team, and my team had no idea what I was talking about. I went in one day and said, I've written this language. Here's the language. I'm fed up with you not being reproducible. And I said, you're going to walk around the lab like this, one-way system, this. And they just looked at it and went, you're insane, go away. So I went away and went, oh, okay, I'm sorry. Went back next day and said, can we make some robots instead? And they went, that's better. And so what I did is I designed the robot, which was basically based around the batch machine, a state so that on-off single object, pour the liquid in, have the correct part, and then the object was connected to other objects really precisely on a graph. So I realized I had a state machine, like an on-off machine, like a switch, a state machine. And then, I'm really inspired by, I guess I should say, it's a kind of a more of a, it's a story now, but I did actually try and build it. I'm more of a computer scientist than a chemist. I tried to build my first computer when I was 8-9 years old. And I took a washing machine apart and telephone, perfectly good functioning washing machine and telephone. I needed the relay in the telephone and the register in the washing machine. I was trying to make a memory function, and just like I had a mechanical idea of doing computation. It couldn't be that hard. And I designed it, put it all together, and it did not work. And then I put the washing machine and the telephone back together, and they didn't work either. So my parents went, here's a ZX81. And also they gave me a chemistry set for some other random reason. I had this ZX81 with 1K of RAM, and all I could do was hit on this keyboard. It did nothing except, I could probably put in a really crappy car game, which would take hours of typing. And I had this chemistry set, which I could never get to read. And I was thinking, I'd really want one to control the other. So actually, I've been thinking about this for many years. So when I designed the computer, lots of people, there's one of the hammering I got from a reviewer this week, said, your computer idea is not new. There's loads of pneumatics doing chemical engineering. There's loads of microfluidics doing chemical engineering. There's loads of robotics doing this. Oh, not new, not new, not new. And I was like, okay, but has there been a hard link between the concept of the reaction and in the reactor, and then the workup after the reaction, and then the separation and the purification? And I looked in the literature and no, there hasn't. And so that's why what happens when everyone does chemistry in these robotic ways, they are very, very fixed to one process. You're going to do one thing. If you do anything else, it breaks. And so the computer was designed to be a universal robot to do any chemistry. It's a very long-winded answer, but I'm really excited now because I think I've convinced myself that the abstraction is Turing complete, if you like. What do I mean by that? Well, a Turing machine is a concept of a simple way of instantiating a computation, and there are certain rules it has to obey. But if those rules are obeyed, then Turing showed that you can basically build any computation in his computation. So we kind of embraced them. And what I wanted to do is I saw that there were all these different chemistry robots all around doing all different things, but not talking to each other. If I could make a Turing complete chemistry robot, it would help them unify them. So it could suddenly do all of chemistry in one machine conceptually. And that's what I've been working for the last few years to do. And so computation is the process of taking a code on a universal abstraction of chemistry called the computer, and turning that code into a molecule reliably every time. But it doesn't matter what hardware you use. Your hardware, just like a digital computer, whether it's a Mac or PC or wristwatch, it has to do the same thing. That means the abstraction has to be properly connected to the code. And that's what the computer is. It's the first time that's been done. Hasn't even been done in biology, right? Synthetic biology is they've kind of deluded themselves, well, not deluded, they're using, quite rightly, the power of molecular biology, of writing genes and so on, and DNA protein translation. But this hard link to the unit operation. So you stuck the poor biologist having to mop stuff up in the lab. Not as much as a chemist. There's more labor in a chemistry lab, I think, than in a biology lab, but I'm not 100% sure.
There's an inflection point here in our scientific society or whatever that I think is worth calling out. And the closest analog, I think, is the internet and the web. So one cool thing about the internet and the web is there's some standards. So HTML, CSS, JavaScript are standard programming languages, or programming language and markup language, et cetera, for the web. And so you use these simple tools, you can make whatever you want. And so now millions of people have access to creating things.
Yeah.
What's really cool about that, the platform and the empowerment of a large population of people, is that you get a huge variety of things that emerge from that. In this case, websites, apps, applications, et cetera. And there's a cool thing as a developer, when I'm building something, I write the code, I press Alt Tab refresh, and then I look at what I've done. And I go back to the code and I fix my mistake. Alt Tab refresh, code some more, Alt Tab refresh, code some more, Alt Tab refresh. My testing cycle is seconds. It's seconds long. And the testing cycle in any scientific discipline is not seconds long. It is months, years, weeks, days, it's long, hours at least. And so what will be really cool to see is if in synthetic biology or in chemistry or in other realms, we get a shorter and shorter testing cycle. If the testing cycle gets short enough, the work of creating things no longer requires a scientist or team of scientists. It can be done by hobbyists. And once you're there, the diversity of things you can create should explode.
Yeah.
Yeah.
And I mean, one of the things we've done with this is that to start with, because I didn't really quite understand I had a formal abstraction. We got lucky. I made some decisions which I think were really fortunate. I based it on the round bottom flask, the batch. All literature is batch. All chemists today that make new molecules use batch. There is flow. That's number one. So it's kind of cool. So it's a hard link I can make already.
Yeah, just to make that clear. So batch system as opposed to a consistent flow system. So in a constant flow system, like a recycling machine, for example, you constantly throw in trash and then it runs the recycling operation and constantly puts out whatever. That's a constant flow system. A batch system is you throw in a batch, you run that one, create the output, then you empty the machine, then you do the next batch. So.
Yeah. And the nice thing about a batch system is you can also speed it up and it can literally emulate flow or ostensibly be a flow, but it has nice mathematical properties when you go from batch to flow. Because continuous, you have this continuous geometry, right? So that's another thing. And then I realized with the abstraction work, and when people were kind of, the problem in chemistry is very competitive, all scientific disciplines are very competitive. But in chemistry, the competitive edge is in the way that you might make something, some ideas there. And so I'm not saying that chemists have a bad culture. I'm just saying that egos in sharing in chemistry is not quite there. The incentive exists for being first rather than being maybe best. I mean, incentives happen over a longer time. So I think that I'm noticing that a little bit. So one of the things I've done is I've created KDL-standard.com, and you go to KDL or xdl-standard.com. That is the schema or the map that allows you to program a chemical or computation machine to make any molecule, and that is free for commercial and academic use. I'm going to maintain it. I'm going to hopefully chemify. Hopefully he's going to use it. I'm going to try and I see KDL to be the engine of materials, chemistry and formulation, even synthetic biology. And KDL is to stuff what HTML is to the web. And that has to be enabling. So it has to be free, because and then we'll build on that. And people will make money, people will do open source, people will collaborate. But wouldn't it be great if I can invent a molecule in my lab tomorrow and give you the KDL code, and you can make it in your lab the day after just by doing Alt-Tab. Boom, boom, boom. There you go, there's a molecule.
So the software is a language standard. That's easy, that's shareable. And then the hardware is, so now you have to distribute hardware so that people can, yeah.
The other thing, so this is even better, right? One of the things I have to do, this is one of the reasons I had to start a company, is that hardware, is it just about Lee Cronin's computer? No. It's about computation. I didn't invent computation. Turing invented computation along with Justus von Liebig. I just realized it was already being done. So, okay, I've got to get credit for something for once, right? And just watch something, right? And so suddenly, all the hardware that people have in their labs already does this. The only barrier is the hardware tends to be vendor locked and is not easy to connect it together. But now I've provided a tool where you can say, I've got this hardware, I'll put it in, draw a graph. Does the KDL compile? Yes, tick, you can make it. So what's going to happen over the coming years is that people already have the hardware. Right now, the barrier to doing robotics and chemistry is a few $1 million. I reckon I can get it down to the cost of a round bottom, a stir hot plate, which is say $1,000.
Can I buy one?
As long as this is the other big question, right? So you bring technology, then suddenly you have all these hobbyists trying to make drugs in their backyard. They could always make drugs in the backyard with a chemistry set. And so what I've got to be very careful to do, but the nice thing about KDL is that we do this properly. We'll have KDL allows you to be safe, collaborative, and also descriptive, right? So there will be points at which, say if pharmaceutical companies might be qualified to use certain KDLs, or, you don't want people making chemical weapons. And so, as a society, we need to ask ourselves whether you're on the left or the right or the up or the down, depending if there is up or down. I'd love there to be an up or down. Right now, it just seems to be boring. Liberalism, no liberalism. I want to be in the middle. I want to make stuff happen. But one of the reasons why I love having discussions like this is I actually say, hey, I could make a robot that's going to cure cancer for you, your personal medicine, but also it may enable your unborn child in whatever number of years to make drugs and potentially harm themselves. How do we deal with that? What do we want to happen? And I don't want to shy away from that responsibility, but in the same way, it's my responsibility to make the technology and to do the science. It's not my responsibility to work out what society will do wrong. In the same way, when that Eurowings aircraft was smashed into the Alps, when the pilot locked the other pilot out and set the altimeter to 0, of course, if the software engineers are thinking correct, we should code in, if flying above a mountain and someone tries to put the thing down to 0, we won't allow that. And that type of stuff we'll put in the computer, right? If someone's going to mix these things together, it'll explode, we'll have a little blacklist and say, no, don't do that. You don't really want that to happen. And so there's kind of things we can do by having those discussions, whether it's in the same way that I'm sure Elon Musk doesn't want people to die in the hand of Tesla. But the fact is, Tesla's going to save many thousands of lives, because what are there on the roads, deaths in the roads in the US every year? 30,000 lives lost. And as soon as one life is lost with Tesla, up in arms. Same like how many drug overdoses are there in the US every year, and in Scotland for that matter? If people could have access to technology and they didn't drug overdose, would that be worth anything? I think it would, right? So, but society has to debate that. I'm paid, or I love to do science, and I want to do it responsibly. But with the UK, we are talking about responsible innovation, which I just think is a kind of a really core thing that I don't support. Because what it does, it stops me from, I've had an idea that may be used for bad one day, and I won't think about it. So the responsible innovation is really a kind of idiotic thing, but maybe that's
there's a fascinating problem. It's more of a meta problem, and it comes up in a variety of places. The one you've just described, in its conception, in its general conception, it's that technological and capability improves exponentially. The distribution of that that technological capability is more and more accessible. And so destructive force comes along for the ride. And so at this point, anybody who wants can go get some fireworks, or anybody who wants can go get some gunpowder. But, zoom forward 100 years, 200 years, anybody who wants can write an algorithm that for, self-replicating nanomaterial that can be really dangerous. Right? Yeah. And it's not just malintent we have to protect against. There's also just a mistake. Like, oops, I forgot I forgot to close my loop. And now my nanotech is replicating uncontrollably in my lab. It's taken over the garage and the kitchen, and I don't know what to do,
So the nice thing about openness is why open innovation is really good, is that you don't have stuff like that because you have the Darwin Awards, right? It's that people select themselves out of existence very early on. Look, so what has saved, I think, exponential computing technology from complete disaster? The openness of the web. Had any one organization had a domain over the web, it would have been attacked and brought down. The fact you cannot bring down websites here, it's a bit like the ribosome in biology. People worry about life on Earth stopping. You're going to have to be pretty damn good at stopping the ribosome. And some people say, oh yeah, we could make a magic self-replicating molecule that inhibit the ribosome. It'll be game over for life on planet Earth. But it won't, because biology's already searched for that for 4 billion years. And it's make sure that chemistry on Earth is not really capable of making that object. And sure, I mean, never say never, but I've never seen runaway catastrophes like this. And I think probably the human imagination is too big at imagining the negatives than understanding. So the negatives which require net protectionism versus openness. I believe open innovation will solve most of those problems. I'm not saying unfettered, unregulated innovation. I'm saying open.
Right. Yep. Yeah. Important distinction. The other way to conceive the previous statement you made was the forms of life that did have vulnerabilities to, these skeleton key destructive mechanisms aren't around anymore because they had those vulnerabilities. And so the ribosome, for example, is robust enough to exist in a high complexity world, and it is protective against that. So there may have been forms of life at some point that were extinctable with these mechanisms, and they are extinct. So
yeah,
cool.
I think would find it really hard to engineer. I mean, I probably a virus that would wipe out humanity, because basically you just go, oh, that's bad, let's isolate, and then the virus dies. I mean, and I know there's lots of argument about COVID-19, lab leak, hypothesis, gain of function, all that stuff. And some of that may have some merit, some of that may be just ludicrous, some of that may be we just don't know what's going on. The fact is, viruses they have an objective in mind, which is to propagate and to stay propagating. And it's like any technology. If technology is kind of resting on us, if the technology has a life of its own, living through us, then it wants to carry on. There are bad elements. I mean, I don't know. I mean, I'm sure someone from Responsible Innovation in the UK will explain to me where this comes from. But I think it's an irresponsible thing to basically stop your best minds from thinking crazy things because of the harm they might do in some unthought scenario, rather than say, actually, knock yourself out, we've made this. Look at all the plastic in the ocean. We should clean it up. And what we're going to do now in the next 50 years, I'm sure we'll clean up the ocean. What we do at climate change, I'm sure we'll remove the CO2 from the atmosphere.
I absolutely agree. I think the arguments against that approach are fear-based. They're fear-based, and they're sometimes just backwards. They're cases made for going back to a previous, and it's like, we can't. You can go back to a previous, and you doom yourself to a different kind of extinction. You have to go forward.
There's always the bad actor. So I don't want to pick on, say, science saying, I don't know, let's say Russia or China or another state, which is secretive. But isn't it more useful if I make a crystal meth machine by accident in Glasgow that the authorities know about, so we can understand how to regulate it, understand how to discuss with society, what do we need with this, rather than fearing that someone else is going to do it in background and then sell it underground or something else. I think there's so much to be gained by treating normal people intelligently with respect and saying, what would you like? And we're failing to do that with the current kind of social media and the arguments about vaccination, anti-vax, and, big power. But we need to sort that out. The internet is the first problem. Like, we invented the printing press, we created a problem. We created the internet, we've got this problem which is critically undermining democracy. I'm sure we will solve it. It's not going to be pretty, because look at Brexit and the fact that, you can't buy petrol in the UK right now because we haven't got any truck drivers.
Oh, man. Yeah. So there's a thread here on plastic in the ocean because I'm working on a project on one. So I'd love to pick your brain on that after we wrap this up.
Okay.
But I know we talk about consciousness. So I wanted to give you a second before we close, if there's anything you want to say about, well, what does it mean to be a conscious human being? How did consciousness emerge? We talked about gravity, the gravitational constant.
My thoughts on consciousness vary according to my consciousness. And my most kind of boring view is that consciousness doesn't really exist, and that it's a kind of an emergent thing that we call a thing that emerges, that we say doesn't exist. And I think that emergence as a phenomena doesn't exist. What we mean with emergence, we're talking about high complexity, high MA things. Things with memory are emergent. Okay, but anyway, going back to consciousness. So the whole thing with consciousness is that it's a very special phenomena that I don't quite understand, and no one understands. And I think it is related on this chain, obviously, the origin of life, multicellularity, intelligence, and consciousness. And then maybe even novelty generation. They're all kind of connected together. But for me, that consciousness seems to be this thing that allows us to understand where we've been in the past, where we are in the present, and imagine the future. And that consciousness builds abstractions. So I think consciousness might exist as a thing because it allows us to do the following thing. I can invent an object in my mind abstractly. Let's say I invent a new type of computer, maybe one that can, deal with, different types of solids or something that don't thought about. And I imagine that. Then I can go to my students and my postdocs and designers and say, look, I've got this idea, what do you reckon? And they might design it with me. And suddenly I take something from my consciousness and I affect the material world. So there's literally, my imagination affects causation in physical stuff. So I'm kind of convinced, I think, from that degree, consciousness is a real thing. And it actually is a bit more important than maybe I would kind of given it credit for years ago. Because, the same way Elon Musk imagined, or someone, it might not be Elon, but SpaceX lands rockets on legs. Someone had to think of that. Got these rockets coming back, and planet Earth can put out anti-accrete even more quickly. Now we've got these rockets on legs. So I think that the role of consciousness is super interesting. I don't think that consciousness is going to be simulatable in a silicon computer anytime soon, but that's another whole podcast. I do think it's material, but I think consciousness is a thing that emerges. So you and I, we don't really exist, right? Consciousness doesn't really exist other than to create abstractions. And I think that, this is why someone was saying to me, it wouldn't be great if we could have dinner with Sir Isaac Newton. It's like, well, yeah, but we're now in 2020 or 2021. We were having this in 2020 on Zoom, big pandemic. I was like, but that's a really silly question, because Isaac Newton's died. And since then, his ideas have propagated around the globe, and they've influenced you and I, and we act differently. So we can't actually have dinner with Sir Isaac Newton, because we wouldn't, it's actually a strange thing to say. And then I went on to explain to him, and we had this argument. I don't think we exist, we are alive. But what I do think we are right now, I have my maximum causal power when I'm alive. What I could do is I could work out, so you just heard my kids there and whatever, I could work out, put Easter eggs in my will or in various organizations I might construct before I die. So when certain events are fulfilled, certain things would happen. So I continue to act in the future as a result of stimuli. I think that's quite cool. And so from that regard, we aren't really ever alive or dead. What consciousness does, it gives us immediate feedback to look after our beings, and also to have maximum power to affect things. And I think that from that point of view, consciousness is both doesn't exist, but really does exist, and you should use it. And use it now, and don't just walk to work the same way every day. Wear different colored trousers, ask different things. Basically, mess with your consciousness to see where it takes you.
Absolutely. What a wonderful note to end on. So open advice to anyone listening on taking advantage of your consciousness while you still have it. Lee, would you let people know where to find you online? What are some things you'd like people to pay some attention to?
Yeah, so I'm online. My website is croninlab.com. You can find me on Twitter at Lee Cronin, and by email, which is easy to find online as well.
Absolutely. Okay, great. Thanks very much. So I have at least 18 more questions that I can think of. So if you're up for it, would love to do this again sometime, maybe a year from now or something like that. It'd be lots of fun.
No worries.
All right. Thanks very much. Lee Cronin, everyone.
Thanks very much.